So my title has a couple of meanings, actually. First of all, proofs about programs. In particular, these three algorithms, which have a number of things in common, not the least of which is that they're all objects of Alex's affection. They're also all very simple in terms of lines of code, but at the same time complex in terms of being built upon sometimes many layers of abstractions, of abstract theories. In the case of Euclid's algorithm, it's natural number, arithmetic, and ordering properties. In the case of the other two, I'll talk about generic or abstract versions of the algorithms that are built on various abstractions, monoid, algebraic structure, strict weak ordering, relational structure, and computational structures like ranges and iterators. You'll hear echoes of some of the earliest papers that Alex and Deepak Kapoor and I worked on in the 1980s at GE. The actual code in the talk is going to be based upon material from a textbook that Kostas Akoutis and I have coming out later this year. And the subtitle of the talk, a computer-based approach, of the book, a computer-based approach, has to do with the fact that almost all of the examples and exercises in the text are written in a computer language, proof language, that's machine checkable. That language is Athena, and this is where the second meaning of my talk comes in, that you write proofs in the form of programs that are executed to either give you a theorem if you followed the rules of inference and axioms correctly and cited them correctly, or it just gives you an error. Well, there's a third possibility that it can go into a loop, but mainly we execute programs to try to add theorems along with axioms that you've added by assertions to an assumption base, which is a stack-like structure that the system maintains. That's only one of the three languages that are involved in Athena. Of course, you have the logic language, which in this case is multi-sorted first-order logic. It has parametric polymorphism and sort inference, so you rarely need to actually write down sort annotations. And there's a pretty nice conventional procedural language, too, scheme-like in a lot of respects. The basic underlying syntax is also prefix notation, but overlaying that, you have a nice way of introducing infix notation and keeping that entirely configurable. So let's talk about Euclid's algorithm. Actually, another title that I thought about for this talk would be 3 Deductive Journeys. But unlike Alex's journeys, I only have a few minutes for each one, so they're going to be more like flyovers. So in Athena, we can express Euclid's algorithm as a recursive function the usual way. We use, in this case, a fun function-defining mechanism that's similar to ML's fun, but it actually outputs a couple of axioms or sentences that you can treat as axioms, put them into the assumption base. So it's the usual recursive definition in terms of repeated mod operations. And the specification we express at the bottom here, that Euclid of xy is a common divisor of xy, and any z that's also a common divisor divides Euclid of xy. So in that sense, it's the greatest common divisor. Now, I'm not going to actually give the proof in these slides of that correctness theorem, but rather talk about some of the underlying theorems and a couple of proofs about the arithmetic operations and ordering operations that are involved. So first of all, you have division and quotient and remainder defined by each by a couple of axioms. And they are recursing using subtraction operations until you get down to a remainder that's less than the divisor. You also have the divides predicate, which is also introduced by a couple of axioms. Actually, more frequently you see an existence sentence like this defining divides, that there exists a z such that y times z is equal to x. But instead, we use these as the definition in terms of the remainder being 0, because you can actually use these axioms written this way for evaluation. You can test the axioms, test your function definition before you go to the trouble of trying to prove something about it. You'd like to look at a few tests and see if they're coming out okay. And yet at the same time, we want to go ahead and prove this characterization sentence as a theorem because it turns out to be handy in proving a number of other results about this divides operator. In particular, here's my first proof example, a tiny example of proof of showing that divides is reflexive. So it's written in terms of a chain of implications. So, and this is one of several forms of chaining that you have in Athena that allows you to write proofs that are highly human readable as well as being machine checkable. So in this case, you start with a little theorem about times. X times 1 is equal to x. The 1 here gives you a witness for the existence statement. And then that, in turn, by the characterization theorem on the previous slide, gives you the result. Here's a larger proof about a cancellation property of division. And it's written, it's a proof by induction, and it's written using this by induction form that's built into Athena. And so you can set up the basis case, x equals 0, and the inductive step going from x to successor of x. In the basis case, I've used an equality chain. In the inductive case, I've given a name to the induction hypothesis, which is actually put into the assumption base automatically by Athena, but I'll name it for use in the theorem, use in the proof. So here I've used force. Might be called Darth Vader's favorite proof method. So what it does is just enter its argument into the assumption base, treating it as a theorem, no questions asked. Blatantly unsound, but a handy feature for writing a proof sketch so that you can actually execute all of this proof. It'll say it's a theorem if, in fact, the other part of the proof is correct. If you've made some mistake up here, then you'd be able to check that without actually completing this part. On the next slide, I have completed the induction step. And that starts out using a backwards implication chain. So you start with the goal. This is to prove a little auxiliary result. Start with the goal and work backwards from it with implications till you get to true. And then that's used, that result is used down here somewhere along with a lot of properties of arithmetic and the induction hypothesis to, in an equality chain to finish off the proof. So the last example for division and so forth that I'll use is what's commonly called the division algorithm, although it's actually just a theorem about quotient and remainder. And this proof is done by strong induction, or it's also sometimes called complete induction, where in the inductive hypothesis you assume the statement is true for all previous values, not just the preceding one. And strong induction is not actually built into Athena like that bi-induction form was for ordinary induction. But you can program it, and we do have it as a library-defined method that you can use. So it takes, it's called the strong induction principle, and it takes the goal you're trying to prove, and then you write a method yourself. Methods in the language are very much like procedures, but only prove theorems. And I've written out most of the proof here, but there's one case where I've used the force, so it's an incomplete proof at this point, and I won't show the rest of it, leave it as an exercise. That's what we do it in a lot of cases in the textbook, give a partial proof and then leave it as one of the exercises. So let me go on to fast exponentiation. So this algorithm computes a to the n in approximately log n steps using a method that the ancient Egyptians knew for multiplication. They were doing addition steps, but if you use multiplication steps, you get a power operation. And I know some of this history from Alex and Dan's beautiful book, From Mathematics to Generic Programming. So the problem that you encounter here is that simple versions of the algorithm do unneeded multiplications. In particular, they might do a multiplication at the end and throw the result away. And if the cost of multiplication is growing with the size of the operands, that can be pretty bad news. You might spend more time on that last multiplication that's useless than on all the other multiplications together. So a very nice solution to this problem that's given by Alex and Paul in Elements of Programming. And their version avoids the extra multiplications and is generic. It works for any monoid. So to do the same thing in Athena, of course it's done with C++ function templates in their book. To do the same thing in Athena, we first of all are able to define a series of refinements of theories to give you algebraic structures like semigroup, identity, monoid, group, ring, integral domain, and so on, where at each theory refinement you're either adding axioms or combining previous theories. So for example, monoid combines semigroup theory, giving you the associative property of this plus operator, and identity theory. And by the way, I'm using plus and 0 here, but such a theory is specializable to any, you can map any operators like times and 1 as long as they satisfy the axiom and apply it to that. So the fast power algorithm, it's programmed in Elements of Programming with 3 function templates, 2 of which are mutually recursive. And of course, internally they use conditionals and while loops. Here we use a couple more recursive functions to exactly mimic the flow of control through the computation. The main function, fast power, just handles the n equals 0 case and hands off the non-zero case to another function. And it, in turn, hands off, there's a lot of mutual recursion going on around here, based on the parity of n until you get down to either n equals 0 or n equal 1. So to prove correctness of that, we specify a correctness property. Is that me? A correctness property of each of these functions, and by proving them and getting down to the main function here, we are able to show that it computes the n-fold application of plus, which could be, as I said, could be multiplication actually to give you the usual exponentiation. Those proofs are by strong induction. Let me just get rid of this. So that's all I'll say about that. Let me go on to binary search, the last example. So I'm talking about the version of binary search on a range delimited by iterators, as in the STL. And in particular, I'm talking about lower bound, which takes two iterators, I and j, and a value to search for x, and looks for x in that range. And so it computes the midpoint and recurses into the upper or lower parts of the range according to the comparison it makes with a memory value at that point, midpoint. So I'm using m here to represent memory, and this double backslash operator is a way that we have of combining a memory argument with the usual arguments, just I, j, and k, of that function. And so there's a whole memory theory underlying all of this. And I'm going to skip that slide. It basically just said something about there are various different ways of specifying this, some of which are easier to reason about than others. And the way that we have in the textbook is this, that this is the specification, and then we do the proof that the implementation I showed you actually satisfies this specification. And it has several conditions and then some consequences. The first one says that for the range from I to j, it actually represents some range. R is a range variable here, and I haven't shown you exactly what a range data type, how that's defined, but basically it's a way of pointing to a particular position and then backing off from that through back operations. And some of the other conditions are specified in terms of that data type, like the ordering, that you have non-descending order, which is generic. And the first conclusion of the theorem is that k actually points to something in the range, or it's equal to the end of range iterator j. And then the other two show the relationship between the value x and either the predecessor of k or the memory value at k itself. There's a slight variation here required to prove this, because the range type is not natural numbers, but the strong induction method that I showed you before was just for natural numbers. But we can map from another range type to the natural numbers with a measure, in this case the length of the range, and plug it into this measure induction method to get the proof. Well, not to get the proof, because there's a lot of work to get the proof. there's a lot of complexity dealing with these boundary conditions, basically, and, of course, the many abstractions that are underlying it. Just a couple of slides about the abstractions that come in here. You have the relational abstractions, starting with binary relation and irreflexive, transitive, through partial order and total order. In this case, what we need is well, I skipped over it. Strict weak order. That's what we need for correctness of this algorithm in the most general sense. The other main set of abstractions is iterators, and they are set up pretty much as you would expect, starting with trivial iterator, continuing by adding operations and axioms about them to forward iterator, bidirectional, and random access iterator. In the case of trivial iterator, it just has one deref operation, but it's also built on refinement of axioms about ranges and memory itself. So I'm really happy to be here, and we brought along some of Alex's long-time friends, namely algorithms and abstractions. Alex has had many very deep insights about such creatures, and he has helped me and many others to come to a better understanding of the beauty of the way that these algorithms and abstractions connect to many basic properties of mathematics and computation. So in the textbook, we use proofs not only as a means of proving correctness, which is pretty useful, but more importantly, we use proofs, we try to use proofs to give aids to understanding and try to spread around some of this deep insight